Hello everyone, myself Yamuna Pagil. Welcome to Yamuna's physics classes. Today we are going to discuss the topic 10.7 Polarization of lesson wave optics. Now, before going to polarization, we need to learn few things regarding light. In the year 1865, James Clerk Maxwell mentioned that, or he put a theory saying that light is an electromagnetic wave. See, this is a single word written in two portions. One is electro, the other one is magnetic. So, light is an electromagnetic wave, meaning if light is propagating in a particular direction, say x direction, it has components both electric field vectors and magnetic field vectors which are vibrating mutually perpendicular. One is in this plane, the other is in this plane. So, if it is moving in x direction, the light can vibrate with the vectors E and B. E is given by the blue shade and B is given by the yellow shade. So, E and blue shades are vibrating mutually perpendicular. If this is the condition, E, the other one will be B. So, they are 90 to each other. So, vectors are actually going like 90 to each other. Now, in this vector, in this electromagnetic wave, we have electric field vibrations are responsible for the vision. So, we are restricting this vision area or electric field vibrations as this. So, here you can see we are considering electric field vibrations. Electric field vibrations meaning we are considering the vibrations of the electric field alone. So, avoiding magnetic field component, electromagnetic vector looks like a pure transverse wave. So, it seems like a pure transverse wave, meaning it has crest, it has trough. It is vibrating as crest and trough, so on. Now, this we have considered electromagnetic wave, then we are taking the electric vibrations, and this electric vibration itself, this electric vibrations itself can vibrate in all possible directions. So, electric field vectors itself can vibrate in all possible directions perpendicular to the direction of propagation. So, that is shown here. Unpolarized light. Unpolarized light meaning electric field vibrations having vibrations in more than one plane. So, this is the representation of the unpolarized light, means either a vector, electric field vector can vibrate in this direction, all the directions are possible for the vibration of the electric field vectors. Clear? If this is the propagation of direction of the light, perpendicular to this, all directions are possible. All directions are possible. But we represent this unpolarized light in the textbooks or wherever you see, you will see that unpolarized light is having the simpler representation. This is a simpler way of representing unpolarized light. That how comes this to this? The question is, what we are going to do is, you can take any two components, resolved components, and make it a single one. We know resolution. What is resolution? Splitting of a vector into two mutually perpendicular components is known as resolution. So, the same thing, if you put the splitted components into one, you will get a particular direction. So, one directions into two mutually perpendicular is known as resolution. So, put the two mutually perpendicular one, you will get as a single one. You take any of the two which are mutually perpendicular, then you will get the central one. Again, any of the two, you will get this one. Similarly, you can put all the directions into north, south, east, west, like news. All possible directions put into four directions. What are the four? Suppose north, south, east, west. Now again, This is a front view of that. But when you go and watch it from the other side or from the side view, you can see that it's like a plus mark. If you look the plus mark, not from here, from the side, you will see these two joins to a particular point. So this is how you represent in the textbooks where it is mentioned. The meaning of that representation is, this is again unpolarized light. Unpolarized light, the meaning of representation is, here the blue shades shows, this direction shows the vibration is in the plane of the paper. This is the plane of the paper and the vibration is carrying on in the plane of the paper. So this is how it vibrates. Now this shows a vibration which is perpendicular to the plane of the paper. The vibration is exactly perpendicular to the plane of the paper. Now comes polarization. So now once you have understood how to represent an unpolarized light, then you can easily say how comes the polarization. So what is polarization? The phenomenon of restricting. You are restricting all possible vibrations of electric field vectors to a particular plane, and that particular plane is perpendicular to the propagation of light. That's why I told you, if this is the propagation of light, it can vibrate in all possible vibrations perpendicular to that. This representation we have shortlisted to this, or we have reduced to this kind of representation. And now we are taking such a kind of representation here to show that this is unpolarized light. Unpolarized light means vibrations in all possible planes. Now such a light is passed through a tourmaline crystal or a crystal which is capable for producing polarized light. So that is known as polarizer. Polarizer means an instrument or a material which can polarize light. So the term polarizer. So once you pass through the polarizer, suppose you have a beam of light, just pass through a polarizer, tourmaline crystal, and the parallel lines, the unpolarized light which are going through them passes through the crystallographic axis. This dotted line shows crystallographic axis. So if it is parallel to the crystallographic axis, you get a polarized light here. That is known as PPL, plane polarized light. Plane polarized light. Plane polarized light has an intensity I0 by 2. I0 by 2 means if I0 is the incoming light, unpolarized light, half of it, because I told you all the vibrations are summed to 2 vibrations, and again from that you are taking apart 1, so the remaining is single vibration. So the intensity as well comes to half, reduces to half. That is I0 by 2. And here 2 more terms has to be familiarized. One is plane of vibration, the other one is plane of polarization. Plane of vibration means the plane of the board itself. This is the plane of vibration of the board. So this is the plane of vibration where that particular vibration, plane vibrations in the plane of the paper is present, or this is how it has polarized. So polarized light has vibrations in which plane of the paper, that is present in the plane of vibration. But the other one which is perpendicular to that, the vibrations that is perpendicular to the plane, please note the colors. So this is yellow, it is perpendicular to the plane of blue. That is known as plane of polarization. Means in plane of polarization you don't have any vibration, that is polarized. Polarized means what? Restricted. So vibrations perpendicular to the plane of the paper is restricted. It can't go. Once it comes out of the polarizer, this vibration is restricted. So that is restricted plane, that is plane of polarization where you don't have any vibrations. So that is represented by PQRS. Now one more thing, similar crystal, exactly a similar crystal, if you place here, once it is coming out of the polarizer, you place the same tourmaline crystal over here, known by the term analyzer. The term is analyzer. The duty of analyzer is to analyze, just verify whether the light is polarized or not. To understand or to analyze that, you keep another crystal, 2 mm crystal over here, through which the plain polarized light is entering. And you can rotate it about this crystallographic axis. If the crystallographic axis of the 2 mm crystal polarizer and the same analyzer are parallel, we will say pass axis. That pass axis, if they are parallel, you will get the same intensity I0 by 2. But if you are putting it through 90 degree or 180 degree, analyzer, if you are rotating the crystallographic axis of the analyzer through 90 or 180 degrees, you don't have any intensity of light, or absolutely it will be 0. The intensity goes to 0. So the angle of the crystallographic axis between that of the polarizer and the analyzer is known by the term theta. So Malus is a scientist who measured all those things and found a law, I equal to I0 cos square theta. Meaning, if theta has a value 0 or 90 or 180, what will happen? This goes to 0. Means if the crystallographic axes are 90 to each other, this is polarizer, this is analyzer, you won't get any intensity. Otherwise, if they are parallel to each other, so if both are theta is equal to 0, cos 0 is 1, obviously I is equal to I0. So we can say that I0 and I are the intensities before and after. Before polarization I0, after polarization the value is I0 by 2. And I can show it by an analogy. If you have, suppose, this kind of a sheet, suppose you have this kind of sheet and strings are tied here and there opposite side. If you plug the string, you can see transverse waves are traveling through this portion and it goes out. So transverse wave enters crust, trough, crust, trough, crust, trough, it goes like. So suppose this is the 2 mm crystal called polarizer. So it allows the light to pass through. This is a 2 mm crystal. Along the crystallographic axis, light waves, unpolarized light entering, then polarized light leaving. Clear? This is so done with the polarizer. Now the same crystal, same 2 mm crystal with the same portion like cutting, this is a crystallographic axis, you put another one here. One you have here known as polarizer, the other one you have here known as analyzer. Now the duty of analyzer is to analyze whether it is polarized or not. So for that I put analyzer in different axes. So here you have the polarizer, it is there, and through the polarizer you are getting plain polarized light. So the plain polarized light reaches the analyzer. Now I am going to rotate the analyzer in different manner. I rotate it in this different manner. So once it reaches like this, what happens? Here you have crust, trough coming out of the polarizer. But once it reaches here, what happens? This is the only space you have. So this kind of big, huge crust and trough is not possible to enter through this much space. If this much space is okay, it can. But when the space is reduced, it will be blocked here. You will have 0 intensity there. So the angle between, this is the polarizer, crystallographic axis. Here, analyzer, crystallographic axis. Here you have polarizer, crystallographic axis. The angle between the two, polarizer and analyzer, is known as theta. And Malus was the scientist who said I has a value I0 cos square theta. So once again, what is polarization? Restricting the all possible vibrations of a light, specifically electric field vectors, to a particular plane is known as polarization. And the intensity of the plane polarized light is given as I equal to I0 cos square theta. It's known as Malus law, and that was the theta was the angle between the crystallographic axis of polarizer as well as analyzer. Analyzer is nothing but the same tourmaline crystal placed in between this polarizer and the other side where you are receiving plain polarized light. So analyzer receives plain polarized light, whereas polarizer receives unpolarized light. Okay, now let us see how can we polarize by the method of reflection and scattering. So we have just considered light can be polarized if it passes through a tourmaline crystal or a polarizer with specially cut crystallographic axis. But there are other means by which you can have polarized light. Now one is reflection. So for reflection, the light is made to fall on a transparent medium. So XY is a transparent medium. Now suppose this is air and this is water. Sunlight is coming and falling on this surface of the water. A part of the light is getting reflected, the other part is getting refracted. But if you look at it, you can see that here the partially polarized light is the reflected wave. The reflected wave, you can see at times it is polarized, but at times it is not polarized. But the refracted light is fully unpolarized. So the incident light is unpolarized, the refracted light is unpolarized. But if you vary the angle of incidence, you change the angle of incidence, and if you could reach at a particular value known as P, when I becomes a value P known as polarizing angle or Brewster's angle, you can see that the reflected light is completely plane polarized. The reflected light is not partially, here it is partially, here it is completely plane polarized. And also one more thing, the reflected light and the transmitted light or the refracted light are mutually perpendicular. They will be 90 to each other. So from this figure I can say P plus 90 plus R equal to 180. So we know R equal to 90 minus P. And we know N is equal to sin I by sin R. The refractive index by Snell's law is sin I by sin R. So sin P by sin R is 90 minus P. And obviously cos P. So sin P by cos P is equal to tan P. This is the famous Brewster's law. Brewster's law states that the refractive index of a medium with respect to the surrounding is equal to the tangent to the polarizing angle or Brewster's angle. So once you know the value of refractive index, you can find out what is the polarizing angle. It comes nearly 53 like for air-water interface. Similarly, you can do it for glass water, whatever it is. So once you know the value of N, you can calculate the value of P. So this is how you get light, plane polarized light by reflection. Now, this is scattering with atmosphere. Another method of getting plane polarized light is scattering. In scattering, the sunlight is coming, unpolarized light from the sun is coming, and it just hits over the electrons in the air molecules. You know, in the atmosphere we have air molecules where you have atoms, molecules, etc. Well, inside you have protons, neutrons, electrons, etc. This electrons gets, air molecules get excited, so the molecules get excited and the vibrations are happening in various modes. So it can vibrate in all possible directions. So in that particular case, waves are generated in all the directions. But you can see that those rays which are mutually perpendicular to the incident light, only those rays that are coming perpendicular to the incident light gets plane polarized. And if it is passing in the same direction, no polarization. So here it is no polarization. So here it is unpolarized light. Similarly, this again is unpolarized light. But if it is 90, you can get polarized light. Here again polarized light you have. Here again polarized light you have. Other than these two directions, at any other directions, you can see partially polarized light in all other directions other than same direction and perpendicular direction. So here you can see some is polarized, some is not. So it is partially polarized. Here you have fully polarized. And the dots shows polarization is perpendicular to the plane of the figure, and the double-headed arrow shows the polarization is in the plane of the figure. So this is how you get polarization by the method of reflection as well as scattering. So this is the part polarization, and I have discussed what is polarization in the earlier topic. Now we have discussed what is polarization by method of reflection and scattering. Hope it is clear. Thank you for listening. Thank you.